Welcome back to the Gyan course MHPDI-MG 2024 conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. Now the presentation will be addressed by Professor Indrajit Sarkar and Mr. Katru Brikas Verma, who is a PhD scholar under the guidance of Professor Indrajit Sarkar and Professor Monalisa Patnaik Madam. So I request Indrajit Sarkar sir and to address you all.
Okay, so let's start with this DAV demonstration. So now you already had a practical demonstration just over, so you can understand so how the things are different when you are doing simulation. When you are first what it is like this generally what happens when we start learning something, we write on the copy, and what we do is we just draw a single line to show a switch, power electronic switch. Then when we go to this simulation circuit, then we go one step ahead. But when we come to work with the hardware circuit, then we understand it is not that simple circuit as it looks like, but it comes with many associated things. So DAV converter, what I have presented, we have two H bridges, one high frequency transformer, and two DC sources, and two capacitors. So input side, output side. Now here when you see this, then we can see here there are so many components. So we have switches, power electronic switches. Okay, Vikas will explain the components. So we have one H bridge, input H bridge, another output H bridge, associated driver circuit, associated control circuit, and then the power supply that we never draw in our copy, never show in simulation circuit, is associated power supplies. And then we have the DSP microcontroller, and then we have the input and output capacitors, these sources, and this high frequency inductor and high frequency transformer. So this makes the complete thing. And then most importantly, we must be having these MCBs, okay, for protection purpose. And then we have load, and then there are voltage probes and current probes are also there. So Vikas will explain the components what are there, and then we'll execute this in SPS modulation scheme to see how the output will look like, and then in EPS also we'll see how the output will look like. So now it is over to Vikas, so you can explain now.
Thank you, sir. Today we are going to see how we can develop a DAV converter. So first of all, to develop the bridges, we need in DAV converter we have two active bridges. So to develop the bridges, like I used a Semicron IGBT module. In this module, we can see there are two switches. Two switches connected in series. So we can see that when we look from here, this is the upper switch and this is the bottom switch, where this will be act as a one leg. So I use this one. We can see this three terminal is a connector of upper switch, and one is a common like as it is connected in series. One is a common terminal for upper switch emitter and bottom switch connector, and two terminal is a emitter terminal of the IGBT model. So it work as a 600 volts. It work until 600 volts and 75 amps. So I use this IGBT module to develop my bridges. So before operating this IGBT, we need a proper gate drive circuit because we have to protect it, and we have to operate it in a proper way. So for that we use a Semicron. This is the gate driver circuit. This gate driver circuit has different some features, like it has one primary input and two secondary input outputs. These outputs are one is for upper switch, and another one is lower switch. It has a short circuit protection, like it will give a dead band, like without we are not we can't so it will by its own self, like internally it give a dead band between the switching pulses to both the IGBT switches. So because of that, if there is at a time if both switches are getting on, there will be short circuit. So that thing it will give a protection by giving that propagation delay, providing between the two switching sequence of the both switches. And also it has a if there is a pulse which is less than 365 microseconds, it will not allow it. So it has that production short pulse detection will be there, so it will not allow it. And also it has a so this gate drive circuit input it requires 15 volts. So to on and off, like to on and off this IGBT modules, it will give 15 volts to the gate to make this IGBT on, and it will give -7 volts to make it off. So that everything, whatever the protection, if something error is there, this protection circuit, this gate drive circuit will off the circuit at that moment only. So it will not allow the switch to get short circuited. So this is the gate driver circuit. See, these are the power supplies to these ICs, where this IC will get a power supply from here, and and also it has a and it will operate till 50 switching frequency of 50 kHz. So you can see, so it is under voltage. It has an under voltage protection. It has an under voltage protection. Like if it is 15, the required input voltage is 15 volts. If it is less than 15, like around 13.5, if it is less than 13.5 threshold voltage, it will get off. So that kind of under voltage protection is there in this, and also. Dynamic short circuit protection, as I told that it will not take any time, so it will instantaneously, when if it is a short circuit problem, it will instantaneously it will off the switch. So we can see the one main criteria is that it has a top bottom interlock dead time. The interlock dead time production is there, so it will give dead time between the two switches. And along with the dead time, it will give on propagation time delay is also there. See here, interlock dead time is around 3 to 4.3 microseconds. So, and also along with that 3 microsecond dead time, I will show you how it is giving. I will give a pulse with a 50% duty cycle. But after going to that switching sequence, that 50% will be reduced because of the dead time that which is providing by this production this gate driver circuit. So, and again one thing I am using is that PWM board. So PWM board, this is a PWM board for to give the pulses from because of this this microcontroller, it will generate 3 volts, but we need a 15 volt pulse. So for that we need a PWM board. So it will when we give the input to this, it will give to this circuit. So this one, this is these are the isolation. 67137. This is an isolation. See, this is a photo isolation. Photo coupler, where it will provide the each isolation. This is for the 3 legs. This is for one leg, this is second leg and third leg. This is for 3 legs. It is controlling for the 3 giving the pulses to the 3 legs. So this is the isolation from this board. We are giving an isolation for this, and this is the NOT gate. Like as these are in 180 degrees phase shift, should be operated in 180 degrees phase shift. So there is an optocoupler. This is a NOT gate, where when the pulse high will come, it will make it as off. So we have 3 B dash. B is when high pulse will come here. B dash means it will be low pulse, like with 180 degrees phase shift, it will make that one. This is the level shifter. So this is the level shifter. It will make a pulse into 15 volts. So how this chip it will be operated for 5 volts, and this optocoupler, this photocouplers, it will we have to provide 5 volts to operate it, and this NOT gate also we need 5 volts, and for this level shifter we need a 15 volts. So this power supply for this is given by this Morrison power supplies. These are plus or minus 15 Morrison power supplies, and also we will get 5 volts. So these are the power supplies to give the power to this PWM board. So now, and also we need a snumper circuit. These are the snumper capacitors which are going to protect the short circuit valves, and these are the snumper capacitors. So now I am going to explain like how I am generating these pulses through this DSP microcontroller. So it is a this is the Texas instrument. It is a C2000 family, a Delfino family. It says TMS F283790. It has a 2 cores where we can use it individually, 2 cores. So each core the clock cycle is 100 MHz. So it has 169 multiplexer general purpose input output pins are there. Here we can see these are 169 pins. These are multiplexer, like we can use it as a PWM ports and as a ADC and DAC ports also we can use it by giving a proper input signal to that. And it has a 12-bit mode for ADC signals. It will the ADC signals it will convert continuous signals into the discrete mode and digital signals. And we have 3 DAC modules also there. So each pin will give 3.3 volts. Like we have, if you want to give this is a main controller. If you want to control the DAB converter, we have to provide a controlling circuit in this. So to each pin it will carry only 3.3 volts. If you give more than that, this pin will be get damaged. So for that we need a sensors like to step down it, to scale it properly, to give proper signals to it. And inside we can give, as it is working in a digital mode, so inside we will convert it to a digital and from decimal to hexadecimal, and we can get an output through the DAC. So here I used CCS Studio, Code Composer Studio. So through this I use coding to generate the pulses. So we can see the EPWM, it has a modules like EPWM, enhanced pulse width modulation. These are the main module that which we are going to use to generate the pulses to our driver circuits. So we can see now I will show you how I use it. So I used EPWM1, EPWM2, EPWM3 and EPWM4. These are the 4 EPWM registers that I modules that I use to give the switching pulses to my gate drive circuit. So for that, so how we can know? So it is a GPIO pin. So how we can know which pin is the EPWM1, EPWM2? We have a data sheet. They provided a data sheet to us where we can see. Yeah. See, we can see here. See EPWM. See, it's a GPIO pin 40. GPIO pin 40. It will GPIO 0 when we give a 0 to it. It will act as a GPIO pin. If we give 1, it will act as a GPIO 1A. Each pin it has a each EPWM model will act as 1A and 1B, where we can add with same frequency we can get a complementary signals through each with one EPWM model. So we are using EPWM1 and EPWM2, 3 and 4. So EPWM2A it is at 38 pin, GPIO 02. So here we have to give a command like to enable the EPWM model. So I gave EPWM1 as a 1. So when it is 1, the EPWM1 will be act. So for that we have to give that that GPIO 0 will be act as a EPWM, and EPWM2 is a GPIO 3. GPIO 2 it will be active when we give 1 logic. It will become a EPWM2A will be act. So if you want to use the EPWM3A, the GPIO 4 36 pin, it will be act as a EPWM3A. So after I use one more, because we need 4 signals because we are giving a phase shift between the legs and also between the two bridges. So for that I used 4 EPWM modules. So and I also use EPWM4A, which is GPIO 06 is 80 pin. So I am using 80 pin 80 and also pin 40. Pin 40 and pin 38 and pin 36. These 4 pins I am using to generate the pulse to give to this driver circuit. So you can see that see these are the I am doing SPS SPS control modulation technique. I am using SPS modulation technique. So we can see that we need, what is the SPS? SP is a single phase shift. So we should have a single phase shift, that is from primary to secondary bridge we want a single phase shift. So for that single phase shift, that my first bridge it will be operate like first switch will be on, when it is on, this it will be off. So we have 4 switches, right? So like this, we have one more module will be there. So this is switch 1, this is switch 2, switch 3 and switch 4. And switch 1 and switch 4 will be operated as on at one time, and switch 2 and 3 will be off at that time. So I am giving a pulses that 1 and 3 will be on, and 3 and 4 will be off when it is on. So, and also this say with same modules, I am develop one more bridge where it has the phase shift. There will be a phase shift between the primary and secondary. So we have only one phase shift, because of that it is a single phase shift. So here you can see that I used GPIO 40, 38 and 36 and 80 pins to give the signal. See, we can see this is the for leg 1. So we can see this is for leg 1. See, this is for leg 1. So we can see there is a phase shift between the primary and the secondary. So this is the leg 1, and this is leg 2, this is the leg 3, and this is leg 4. This is for one active bridge, this is for second active bridge. So we can see there is a phase shift between this. I gave 40 degrees phase shift. So here we can't give directly 40 degrees phase shift in this program, like we have to convert into a digital signal. So I gave as 40 degrees for 40 degrees. The digital is 0511. So that it should be in hexadecimal. It is 16-bit register. So EPWM is a 16-bit register. So we have to give in a hexadecimal mode. So I gave 0511. It is the 40 degree will be converted to digital as 0511. So, and also I am operating. So at what frequency I should operate? So I took an operating frequency as 50 kHz. So I am working at a 15 kHz, 15 kHz. So I give like that 50, how we will decide that 15 kHz in this DSP model. That there is a module like so this is the okay. So this is EPWM model signals and connection. This one EPWM block diagram is here. So here our clock frequency is around EPWM clock frequency 100 MHz. So how we can make it as 100 MHz into 15 kilohertz. So here clock prescaler is there. There is an high precision clock division. We have EPWM clock, so we have to divide it. So for divide it, we have a clock prescaler is there. It will be scaled into our required frequency where we can get the 15 kHz. So there is a you can see the clock divider and high precision clock divisor are there. They both are there. So we can see. See these are the clock div and HSP clock div. These are the two scalars. Where if you want 00 as a clock div, if you give 0, it will be 1. If you give clock HSP is equal to 0, it will be 1. So the formula for this is so here we can see the formula EPWM by HSP clock div into clock div. So this is the to decide the time based clock. So at what clock that EPWM should operate. So this HSP clock div and clock div, these are the scaling bits where we can scale. So I use it at clock div 1 and div 1 and div 1. So I will use 1 and this one as a default. That clock div will be 1 and HSP clock div will be 2. So so the formula for this EPWM clock is so so EPWM clock div I use. So from here we are getting a prescaler by using the EPWM clock and HSP clock div. After that it is going to time based counter. So this counter will at what count till what count it should go. So that is important. Like we should not go for infinity. So we should have a proper time counter till what count it should count. So this 16-bit time counter will be counted. So for after that we have to which kind of counter. There are 3 types of counters. The up counter is there, down counter is there, up down counter. So I am using here in my code I am using up down counter. See, TB count up down. So I am using up down counter. So but okay, we can get it in a triangular counter will become. So see this is the up counter, down counter, up down counter. So we can get like this. Okay, if we decide a TB counter, TB clock. So but how we can get the pulses? So we need a compare signal to compare that triangular. It will be decided this by the compare registers. So this compare registers it will decide like at what level. So at what level I have to do the compare because from it is going from 0 to TB PRT. So where I have to compare it. So for that there is a formula for that how at what compare value we have to give. See this is the formula. I will show an example. So compare A. So if I want a compare value, like you can see this is the compare value. So to get compare duty cycle we want to know which duty cycle should be operate. If I want to operate my duty cycle at 20 degrees, so it will be 100% minus 20% into TB PRT. As we by this formula we can find that TB clock is by pre-scaling the EPWM clock. So the TB clock will come, and also this is a frequency of our required. I want to operate at 20 kHz, so I want to this will be 20, and this will be regarding our pre-scaler. So 100 by here it is an example. If I want to operate in 20, 100 by 20 divided by 2. 1 by 2 is because it is up down counter. If it is only up or down, 1 by 2 will not be there. But 1 by 2 because of this up down counter. So 100 by 20 by 2. So it will be my TB PRT. So how I will get a compare value if I want to operate it as a 20% duty cycle. So 100 minus 20 into TB PRT. So I will get. So these are the digital values. We have to use the code. We have to give the digital. We can't give directly the values. Those are the digital values. So like that I decided my TB PRT and compare values. So so how much? So I gave a point. I used 50 degrees duty cycle. So 0.5 into TB PRT. This is because 100 minus 50. So it is 50 degrees. So 0.5 into TB PRT. My TB PRT for 15 kHz is 1667. So I use it for this. So we can see here. So see these are 50 degrees. Means duty 50 on and 50 off. So the whole time is 100 T. This is the T on time and this is the T off time. So I use it as this is 50% duty cycle. So both my first leg is 50%, second leg 50%, third and fourth also 50%. But my phase shift, here the phase shift I gave 511. It is nothing but 40 degrees. So I am getting a 40 degrees phase shift here. We can see. So now we generate the pulses. So we have to check whether these pulses from here we are getting the pulses. So we have to check whether these pulses are going to EPWM, and after that it is giving to required voltage of required pulse to this IGBTs or not. So we will check that one. So I connected to, as I previously said, EPW 1A, 2A, 3A and 4A. 1A is at 40 pin, so I connected to 40 pin and ground. Then after it is 2A is a 38 pin, 3A is a 36 pin and 4A is a 80 pin. So I connected to this. Okay. So we have to give first to operate this this PWM board. We have to give 5 volts and 15 volts. So I will give with this. Okay. So we'll check this one. See. So you can see the pulse is coming with the duty cycle of 50. You can see duty cycle 50, 150. So yeah, pulses are coming. So what about the switch? This switch is getting the pulse 15 volts. Pulse or not? We have to check. So you can see that, is it visible? Is it visible? So you can see that plus 15 and minus 7. You see, you can see that each box is 5. So you can see that plus 15 and minus 7. So we are getting pulses to the switches. So now we will see our space is working or not. So as I previously told, this is the power supply which I am using. So this is the load resistance. So this is the high frequency transformer. As we know, the DLB is the isolated converter. So these two bridges are connected with an isolation, the isolation transformer. This is a 20 kHz isolation transformer from 300 volts to 48, 300 volt to 48. Around the turns ratio is 6.25. And this is my external inductor. So we can see that the leakage inductor where the power transfer will be depend upon this one. So there are different kind of formulas for each modulation, how to decide the inductor values. So now I am going to switch on. So I am giving 100 volts. So I switching on the load, and I am switching on the, so you can see. So you can see, so this is the primary bridge voltage, this is the secondary bridge voltage. You can see the phase shift here, so it is showing 24.7 phase shift, and this is the inductor current. So you can see this 99.8 volt, and the bridge volt 37.1 as the turns ratio, based on the turns ratio, and this is the inductor current. So our SPS is it is working with a phase shift. So now we will check with the EPS. So EPS, what will happen? It is like a square wave, but in EPS what we are giving is, we are giving EPS is extended phase shift. Extended means we are extending with another phase shift. So that extended phase shift will be within the bridge. So we, between the two legs of the primary bridge, we are giving the phase shift. Now we are giving the equal, we are not giving any phase shift in the primary, but in EPS control that we are giving a phase shift. So we will generate in this and then we will check it. So we are giving a 20 degrees phase shift in the primary, within the primary. So for 20 degrees, ours is 5 CA. So we are running. So we will check it. So you can see. So you can see this is quasi square wave. You can see there is a phase shift between. See, it is not a square wave now. See, it is not a square wave now. So there is a phase shift between the legs. That's why it is coming as quasi square. See, there is a voltage becoming zero for some particular time period. So because of that, there is a problem of circulating current in this DAB. So to reduce that thing, we are giving a phase shift where at a particular point we are making the switch short. Means like diodes, there are anti-parallel diodes are there for each switches. So that diodes will make is a freewheeling. It will use work as a freewheeling which reduce that back power flow, which is nothing but reactive power. That back power flow, if it is increased, what will happen? The switches, the stress on the switch will be increased. Because to reduce that one, to increase the efficiency. So this, if we give the phase shift between the legs, so it will make a short there, and it will that bypass that back power flow through the diodes. It will freewheel it. So like that we can improve the efficiency. So we can see that there is a quasi square wave here. So EPS is also working. This is inductor voltage in the secondary waveform, voltage waveform. So this is about SPS and EPS.